Yeah. So really very welcome for to this workshop, and thank you for joining. And we receive a really very good response to this workshop, and it's because all the speakers are very young and emerging leaders in their field. So this workshop is just to celebrate the 10th year of my group in IIT Delhi. And so I'll just take 2 minutes to introduce our group, and then we'll start the conference. So our group is at the Department of Physics, IIT Delhi, and the group name is Spin Dynamics. And in last 10 years, we have been focusing on different areas of spintronics, mostly experiment as well as micromagnetic simulation. So these are some of the topic that we are focusing on: spin orbit torque, spin Hall effect, and so on. And some of the facilities that we have developed, I will just briefly mention here. We have one of the state-of-art AGE spotting system, and as well as an indigenous spotting system, which allows us to grow magnetic multilayers. Then we also have a department level pulse laser diffusion system for growth of oxide material. Then we have a 20 gigahertz probe station that allows different kind of measurements that includes both frequency and time domain measurements of like spin Hall nano-oscillator or spin torque oscillator. And you can also do spin torque ferromagnetic resonance. And we also have a home built FMR setup and magneto-optic air effect. We are also in process of building a microscope. And recently we have also developed this harmonic measurement setup where we have designed a vector magnet, and using that setup we also saw the SOT switching for the first time recently. And for fabrication, we have the nanosclerosis facility where we have e-beam lithography, RF sputtering in the clean room, and several characterization setups are there. I'm just showing one example here, and some also reactive ion etching systems are there. There are many other things in the CRF as well as NRF. I just show some pictures here, but the facilities are quite good. So, and so you all are welcome to collaborate with us, and I hope we can form a nice kind of group on spintronics within our community, Indian community, so to say. Okay. So with that, I will now go to the conference, and let me now share the first speaker's information about the first speaker. Our first speaker is actually alumni of IIT Delhi. Just a minute. Okay, do you see my screen?
Yes.
Okay, so welcome to this first session of this workshop, and in the first section is spin Hall nano-oscillator, and this will be chaired by myself to make it simple. And our first speaker is Himanshu Fulara, who recently joined in IIT Roorkee, and this is his biodata. So he has joined recently in IIT Roorkee, and before that, of course, he did a PhD from IIT Delhi, and then first postdoc at Max Planck Institute Halle, and consequently he worked at the University of Gothenburg, where he did this lot of pioneering work on spin Hall nano-oscillators, and he was involved in implementation of a wide range of application from CMOS compatible microwave signal generator to beyond CMOS spin wave technology and emerging brain inspired computing. So, and he has published many good papers, of course, in Nature and Science Journal. So, Himanshu, over to you. You can now start sharing,
Yeah.
but maybe I need to stop. Yeah.
Yes. So thank you for this kind introduction, and let me just share my screen. So I think my screen is visible to all, right?
Yes.
Yeah.
You can
So,
go to full screen.
yeah, I will just, yeah, it's fine now, right?
Yeah. Yeah.
Yeah, so thank you again. And let me also take this opportunity to congratulate you for your 10 productive years at IIT Delhi. And it's always pleasure to connect with the alma mater via such type of events like this online Spintronic workshop. So as my title shows, I will be speaking about spin Hall and oscillators um, and their applications for neuromorphic computing applications. So before I start, let me just acknowledge my previous group members who have contributed in this work. So Mohammed and Roman has mainly contributed in what I'm going to present today, and Ahmad and Mikola have provided micromagnetic simulation support to the data. And you will see talks from new postdocs who are currently working there, Akash and Nilamini, and they will be presenting their interesting results in this session after my talk. And we have also collaborated with Tohoku University in some of our projects. So I would also like to acknowledge Professor Hideo Ono and Professor Sunsuke Fukami for their excellent collaboration in carrying out this this work. So with this is the outline of my presentation. So I will start with a brief introduction of spin Hall and oscillators, in which I will particularly focus on nanoconstriction based spin Hall and oscillators, and I will show their CMOS compatible operation. And then I will discuss about the mutual synchronization of these spin Hall and oscillators in chains. Then in my second part of my talk, I will talk about how these oscillators can be used for neuromorphic computing. So in particular, I will discuss about two-dimensional spin Hall and oscillators arrays. Since these arrays, these arrays are quite promising for neuromorphic computing applications, but to perform complicated neuromorphic tasks, one needs to have an individual oscillator control. And that will bring me to the final part of my talk, where I will discuss a new state of art of our voltage controlled spin Hall and oscillators. And I will then demonstrate two different mechanisms, voltage control mechanisms, to control the mutual synchronization in a linear chain of 4 oscillators. So let us start with this question, that why do we study these spintronic nano-oscillators? So if you look at the Internet of Things around, you see a huge demand of nanoscale microwave sources for different applications, such as these RF wireless communication, where we need these microwave sources for sensing applications. And then this beyond CMOS wave-based computing, spin wave-based computing, which we also call megnonics. And then this microwave assisted hard disk drives, which were recently launched by by Western Digital in late 2020 of 20 terabyte hard disk drives, where they use these spin-torque nano-oscillators to write the information. And then this emerging neuromorphic computing, where we try to use these oscillators to mimic neuron interactions of our brain. So in all these applications, the common basic requirement is, of course, the nanoscale footprint, and then this faster operation and tunability of the frequency as a function of current and magnetic field. So if you look at these structures, like this is the spin-torque nano-oscillators, which comprises of two ferromagnetic layers separated by insulating or metallic spacer layer, and this is the same nanopillar structures, but grown over a spin Hall material. So if you look at these structures, they basically fulfill all these demands because they can be miniaturized to nano dimensions, and you will see that they are operational at gigahertz frequencies, and they are highly tunable with both current and magnetic fields. And most importantly, their highly nonlinear properties basically allows these oscillators to mutually synchronize, and that synchronization is very much needed to mimic neuron interactions of our brain. So so now let's come to the basic principle of operation of these spintronic nano-oscillators. So if we start from the basics, so if we let's take a ferromagnetic material, and if we place this ferromagnetic material in an external magnetic field, these individual movements, magnetization movements, they experience a torque, and because of this torque, the individual movements starts to collectively process around this external magnetic field. However, due to the magnetic damping of the material, this precessional motion gets damped very fast. And as you can see in this video, that this magnetization vector eventually aligns along the direction of the external magnetic field. So, and this magnetization dynamics is well described by this Landau-Lipschitz equation, where we have a precessional term, and then we have a damping torque term, which opposes this precessional motion. Now, if you can come up with this, with an additional term which can counteract this damping, which we call spin transfer torque term, then we can have a steady state oscillations in the material. So this spin transfer torque term was proposed by Professor Slonczewski in 2000. And now the question is, how do we generate this spin transfer torque? Well, there are two promising approaches to generate this spin transfer torque. In one of the conventional approach, we use structures like magnetic junctions, in which two ferromagnetic layers are separated by a spacer layer, as you can see here. And in such type of structures, we inject an unpolarized charge current, and then this unpolarized charge current, when passes through this one of the ferromagnetic layers, it gets spin polarized. And then when this spin polarized electrons diffuses into the adjacent free layer, then they basically exert a spin transfer torque via the transfer of spin angular momentum, and then excite the magnetization dynamics in the form of these auto oscillations. So so this is one conventional approach, and we call these devices, the spin transfer torque based devices, we call these oscillators spin torque nano oscillators. Now, the another emerging approach, which we can call an energy efficient approach, this makes use of an spin Hall effect. And in spin Hall effect, we inject the same unpolarized charge current through these heavy metals layers such as platinum, tantalum, and tungsten. And due to the high spin orbit interaction of these heavy metal layers, these unpolarized electrons, the spins of these unpolarized electrons gets deflected perpendicular to this incident current direction, and forms a pure spin current. And when this pure spin current diffuses into this adjacent ferromagnetic layer, it exerts a spin transfer torque via the spin angular momentum transfer, and we can see these auto oscillations at very low current due to this spin Hall effect. So my talk basically focuses on these type of oscillators, which we call spin Hall and oscillators. So to minimize this threshold current density, different groups had proposed different device layouts of these spin Hall and oscillators over the years. In 2012, Professor Ralph and his co-workers at Cornell University have proposed the first nanopillar-based spin Hall and oscillators. And on the same year, Professor Democrito, along with Professor Urajidin and Professor Demidov, have presented this nano-gap-based spin Hall and oscillators. And 2 years later, the same group has also demonstrated a nanoconstriction-based spin Hall and oscillators. And then Professor Krivoroto group at University of Irvine have reported this nanowire-based spin Hall and oscillators. Now, among these different device layouts presented so far, this nanoconstriction based spin Hall and oscillators are particularly attractive because they can be fabricated easily, and they offer a flexible device geometry. We can make a chain of oscillators in this geometry, and most importantly, this geometry also offers a direct optical access to prove the magnetization dynamics. And you will see in the later part of my talk that this geometry also offers an individual oscillator control, which is quite crucial for these neuromorphic computing applications. And one can also note this this auto oscillation frequency behavior as a function of drive current. You can see this red shifted frequency behavior, and this behavior is because of the fact that this auto oscillating mode at this constriction region is strongly localized because of this anisotropy configuration in this constriction region. And this localization is not beneficial if you want to synchronize multiple oscillators in a chain. So to address this issue, my colleague Mikola basically simulated these nanoconstriction based spin Hall oscillators in outer plane magnetic fields, and as you can see here that at close to perpendicular magnetic fields, you can see this expansion of this auto oscillating mode in the constriction region. And this expansion of the auto oscillating mode allows the neighboring oscillators to synchronize effectively, and therefore we can have a mutual synchronization of multiple oscillators. And this is exactly what can be seen in the experiments. So here you can see that 9 identical oscillators are fabricated in a chain, and when we inject a drive current, and then you can see that individual oscillators starts to show up. And then as you increase the drive current, these individual oscillators try to starts to synchronize, and you can see that synchronization can be seen as an increased output power and there's a reduced line width. So this was done by Ahmad et al. In 2017 from our group. Now our group has also shown the scalability of these spin Hall oscillators. So in 2017, our group has demonstrated this a truly nanoscopic 20 nanometer spin Hall oscillator device in the outer plane magnetic fields. And you can see here this that a very nice positive current tunability as a function of drive current. Now, to use these oscillators for commercial purposes, one needs to have a CMOS compatible operation. So for this CMOS compatible operations, we basically combined two concepts in which we use the CMOS compatible highly resistive silicon substrate, which offers a high thermal conductivity, with the tungsten, which offers a very high spin Hall angle. And then we demonstrated this this auto oscillations in these cobalt and boron magnesium oxide tungsten based spin Hall oscillators. And as you can see here is that this auto oscillation frequency shows a non-monotonic current dependence, which shows a localization behavior at lower drive currents, followed by an expansion of the auto oscillating mode in the constriction region at higher drive currents. And also these oscillators offers a wide frequency tunability of between 10 to 30 gigahertz at lower drive currents. So with this, now I come to the second part of my talk, where we have extended our earlier demonstration of mutual synchronization in linear chain to two-dimensional arrays. And so here we have fabricated two-dimensional spin Hall oscillators arrays of different layouts, like from 2 by 2 oscillators to 4 by 4 to 8 by 8 oscillators. So we have about 64 oscillators in an area of less than a square micron. And then we perform this auto oscillation measurements in these two-dimensional arrays. So here, as an example, I have shown the auto oscillation in 4 by 4 oscillators arrays, and you can see here that initially these chains of these individual oscillators, they are synchronized. Therefore, we can see these 4 individual signals. But as we increase the drive current, these chains starts to further synchronize, and then we have a very strong signal with a reduced line width. And here we have plotted this line width as a function on number of spin Hall oscillators for different pitch and different widths of oscillators. So and as you can see here is that this line width shows a very nice 1/n dependence of oscillators, which is quite in line with the prediction of the synchronization theory. And this behavior can be fitted by this monobind dependence. And overall, we have observed a reduced line width of 60 kilohertz, which translates into a quality factor of about 1,70,000, which to the best of our knowledge is the highest quality factor reported in such spin Hall and oscillator networks. Now I will change the flavor a little bit. So here I have shown a video clip in which a swarm of fireflies flashes in a synchrony. So the idea of showing this video clip is that to understand how do we memorize an event. So we memorize an event in terms of a pattern of ensemble of neurons, and whenever we try to recall an event, our neurons basically fires at a frequency of about 100 cycles per second. But in the same way as our neurons fires during the actual event. So so basically what I'm trying to say is that our brain basically memorizes the pattern, and therefore we can memorize the event. Therefore we can miss the details of an event, but we do not forget the memory. So so basically this interaction between the neurons defines how we associate to our memory. So so we memorize any event in terms of the interaction of the neurons in a synchronized pattern. And this is exactly how it is shown in this video clip. So the researchers over the last 5 to 10 years have tried to emulate such neuron interactions of our brain with the help of these spintronic nano-oscillators. So in 2018, Yuli Grolier and her co-workers have demonstrated a neuromorphic vowel recognition using a network of 4 electrically coupled vortex-based oscillators. So in their demonstrations, these individual oscillators acts as a individual neuron, and each oscillator is driven by current I1, I2, I3, and I4. Now with 2 independently tunable external microwave frequencies, FA and FB, injection locked to this network, they basically obtained a synchronization map which can distinguish 20 different synchronization states. For example, this 2A and 4B corresponds to a state in which this oscillator 2 is injection locked to frequency A, and oscillator 4 is injection locked to frequency B. So we can have different combinations of this external frequencies to this internal frequency of these oscillators, and we can have these 20 different synchronization states. And then with then they train this hardware in such a way that each vowel, so these are the French vowels, so each French vowel presented as an input to this network of oscillators can be characterized by a certain synchronization state. And by doing this, they were able to recognize these French vowels spoken by 37 different speakers with a recognition rate of 85%, which was quite a remarkable success. But there are downside of this demonstration that it's very complex to extend this this network because each oscillator is driven by individual current, and also since they have used these vortex-based oscillators, the synchronization bandwidth is very small. So we were quite motivated by this study, and we also tried to perform the similar demonstrations using our spin Hall and oscillator arrays. So we use this 4x4 array of oscillators, and in our demonstration, each individual chain basically acts as a neuron. So we have 4 chains corresponding to 4 neurons, N1, N2, N3, and N4, and then we injection locked frequencies FA and FB at gigahertz, and then we were able to reproduce the similar synchronization map, which I have already shown. So which essentially means that our network of oscillators can also perform the similar neuromorphic vowel recognition if we can train such a network of oscillators. However, this training of such oscillators needed the individual oscillator control or the individual chain control. So to do this, we we basically introduced a new type of new state of art of our voltage controlled spin Hall oscillators. The idea was to exploit the perpendicular magnetic anisotropy in the oscillators to control the frequency and the spin Hall oscillator characteristics. So this basically brings me to the final part of my talk. So to basically to make use of this perpendicular magnetic anisotropy, we first introduced these perpendicular magnetic anisotropy based spin Hall oscillators. And in our oscillators, this perpendicular magnetic anisotropy arises from these cobalt and boron magnesium oxide interface. And then when we perform these spin transfer torque measurements to extract the perpendicular magnetic anisotropy field, which is about 0.62 Tesla, and this damping constant about 0.0223. And of course, this spin Hall angle of about 40%. Now, the magnetism dynamics in such pattern thin films is described by this equation where we have this is the auto oscillation frequency and this is the FMR frequency. And then this N is basically a nonlinearity coefficient, the sign of which determines the nature of the auto oscillating mode. For the negative sign of nonlinearity, we have a localization of auto oscillating mode, and for the positive nonlinearity, we have this propagation of spin wave auto oscillations. So here we have analytically calculated the same nonlinearity coefficient as a function of applied external magnetic field and the PMA field. So what this color map shows is that at low magnetic fields for a particular perpendicular magnetic anisotropy field, we can achieve a large positive nonlinearity at low magnetic field, which means that we can in principle excite propagating spin waves at low magnetic fields with the help of this perpendicular magnetic anisotropy. So this is exactly what we have observed in our experiments also, that here we have performed auto oscillation measurements for a nanoconstriction device of 150 nanometer as a function of magnetic field. And you can see here is that auto oscillation excites at frequencies well above this ferromagnetic resonance frequency, which clearly indicates the propagating nature of these spin wave auto oscillations. And this behavior was quite reproducible for other constriction width devices. Here we have shown the similar behavior for a constriction width of 200 nanometer. And we have also extracted the propagation length in our devices using these formulas, which the propagation length in our devices was estimated as 1.1 micrometer. And we have further explored the current tunability of these spin wave auto oscillations. And here we have shown these current sweep measurements for two different magnetic field regimes. One is at 0.4 Tesla and other is the 0.8 Tesla. And you can see that this behavior of this auto oscillation frequency is completely different. This can be understood with the help of the same nonlinearity coefficient color map. So at low magnetic fields, you can see here this nonlinearity is initially negative. Therefore, this auto oscillation frequency decreases initially. But as we increase the drive current, this nonlinearity becomes positive due to the expansion of this auto oscillating mode. And therefore, we can see this increase in the auto oscillation frequency at higher drive currents. On the other hand, for 0.8 Tesla magnetic field, we only observe a blue shifted frequency behavior because this, if you look at this nonlinearity coefficient F at 0.8 Tesla, which is already positive, therefore we only observe this blue shifted frequency behavior. This non-monotonic current dependence was also observed in our micromagnetic simulations, and here we have recorded this spatial maps at three different auto oscillating currents, three different drive currents. So at 0.1 milliampere, we observe a localized auto oscillating mode, which starts to propagate at higher drive currents of about 4 milliampere, and then it starts to further propagate with an increasing k vector at 0.7 milliampere. So this, our micromagnetic simulation also shows the propagating nature of these auto oscillations, and these three behaviors can be summarized in this video clip. So now, having this perpendicular magnetic anisotropy in our devices, we tried to control this perpendicular magnetic anisotropy, or we tried to tune this perpendicular magnetic anisotropy in our devices. So for that purpose, we introduced voltage controlled spin Hall and oscillators. So this is the typical scanning electron microscope image of our gated device, in which this gate was deposited over this nanoconstruction region to apply this voltage. And this actual device is located here, and this is the zoomed version of this region, where you can see this device connected with these electrical pads. And these are the layer ordering of these stacks. So the perpendicular magnetic anisotropy again originates from this cobalt and boron magnesium oxide interface. So so now we perform these auto oscillations as a function of different gate voltages. And as you can see here is that from -2 volt to +2 volt, we observed a modulation in this auto oscillation frequency of about 50 megahertz. In addition, and to our surprise, we also observe a very strong change in the threshold current as we increase the gate voltage from -2 volt to +2 volt. So we extracted this threshold current via the inverse power dependence, and we observed about a 22% tunability in this threshold current, which was quite interesting and which we did not expect actually. So to understand this behavior, we perform the spin transfer torque measurements in such gated devices as a function of different gate voltages. So here I have shown STFMR peaks at 7 gigahertz as a function of different gate voltages. So you can see here is that these resonance peaks shifts a little bit, but also these resonance peaks also shows a change in the line width. And when we extract this effective magnetization as a function of gate voltage, we observed a rather small tunability, 1% tunability in the perpendicular magnetic anisotropy, although the change in the effective magnetization was about 14 to 15%. And we also extracted the line width, and line width shows a dramatic change as a as a function of gate voltage. And we can then extract this this damping constant, which we call an effective damping constant, which shows quite a significant change in this effective damping constant of about 40%. So so to further understand the origin of this the behavior, we went back to the literature, and we found that this behavior was observed in such type of stacks, but the modulation was rather quite small. So we wanted to understand why this large modulation was observed in our gated devices. So then we performed the micromagnetic simulations in our gated devices, because we believed that our STFMR measurements are quite sensitive to this gated region. So we performed these micromagnetic simulations at different gate voltages under this region. And then we observed that for a negative gate voltage of -3 volt, where the PMA is higher, where the PMA is basically higher, we observed a complete delocalization of the mode with the large emission losses into the magnetic leads, which understandably leads to the higher damping in our case. On the other hand, for positive 1 volt, for the positive gate voltages, we only observed a strong localization of this mode, which basically leads to the reduced damping in our measurements. And then we try to extract this effective damping constant values through these spatial maps, and the simulated values agrees quite well with these experimental values, which shows that our mechanism of this damping modulation is reasonably correct. Now, so far I have shown this voltage control operation via the electric field mechanism. What it means is that whatever changes we have observed in our auto oscillation frequency and threshold current, that is purely driven by this electric field. And the gate remains at the high resistance state. Now, if you further increase this gate voltage, so this conducting bridge starts to build up between these between the electrodes and this interface, due to the migration of these oxygen ions from this cobalt and boron magnesium oxide interface towards the gate. And then here we observe a memristive current, which adds or subtracts to the total drive current of the spin Hall and oscillators. So And these low resistant memory system states can also be controlled by the current compliance of our power supply. So here you can see different low resistance states as a function of these different compliances. So what it means is that this voltage control oscillator can work as a memristor, and as well as we can tune the threshold current and frequency with the help of this electric field control mechanism. So here you can see that in the high resistance state, the oscillation frequency is driven by the electric field, and therefore the oscillation frequency decreases as we increase the gate voltage from -2 volt to 4 volt, and the gate remains at the high resistance state. But when you further increase the gate voltage, due to the formation of the conducting bridge, our oscillator basically sets into the low resistance state, and therefore it adds or subtracts current, and therefore the oscillation frequency basically increases. So you can see this switching from high resistance state to low resistance state can be seen via this jump in the oscillation frequency. While on the reverse sweep, this state,
Himanshu,
the low resistance state, yes, I'm trying to now.
Okay.
Yeah, I'm trying to sum. So while on the reverse sweep, this low resistance states remains intact, which shows that this memory functionality also offers a non-volatility in our devices until this gate voltage reaches to the reset voltage, where it follows follows the original frequency. So now finally I will discuss how we can control the mutual synchronization via these gates. So here I have shown 4 spin Hall and oscillators in a chain, and we have deposited gates over these connecting bridges between these oscillators. So M1 is located in a bridge connecting oscillator 2 and 3, and M2 is located in the bridge connecting oscillator 3 and 4. And then first we demonstrated or first we measure this auto oscillation behavior as a function of derived current in the absence of any gate voltages. So as you can see here is that all the oscillators are synchronized initially, and then they starts to desynchronize, and then we have identified these two signals as the signals corresponding to oscillator 1 and 2, and the upper frequency branch corresponding to oscillator 3 and 4. And at this drive current of 0.712 milliampere, where we can see these two separate branches, we change this gate voltage of M1 from -2 to 4 volt, and as you can see here is that the oscillator basically remains in the high resistance state, and as we increase the gate voltage beyond 4 volt, it starts to switch into the low resistance state. Now, if you measure the auto oscillation frequency behavior as a function of gate voltage, as you can see that these two frequency branches starts to synchronize as we increase the gate voltage from -2 to 4 volt, and interestingly, they start to synchronize even in the high resistance state. And when we further increase the gate voltage beyond 4 volt, this synchronized state shows a jump in the frequency. But however, these two frequency branches remain synchronized even in the low resistance state. Now on the reverse sweep, this low resistance state remains intact. So therefore, the synchronization of these auto oscillators remains intact, and until this gate voltage reaches to this reset voltage of about 0.2 volt or 0.3 volt, where these two frequencies, where this signal starts to desynchronize into these frequency branches of F12 and F34. So what I'm trying to make here, the point which I'm trying to make here is that by tuning these mutual synchronization in a linear chain of oscillators, we can tune the synaptic interactions of these we can tune the synaptic interactions of our neurons by using a chain of such oscillators. So with this, I would like to summarize my talk. So I have shown CMOS compatible spin Hall and oscillators operation with a wide frequency tunability. And I have also shown mutual synchronization in both spin Hall and oscillator chains and two-dimensional arrays. And I have tried to show you that how these spin Hall and oscillator arrays can be potentially used for the neuromorphic computing applications. And I have also shown how these oscillators can excite propagating spin waves at a very low magnetic fields. And this voltage tunability of threshold current and frequency is very promising to control the neuron interactions or to mimic neuron interactions via these spin Hall and oscillators. So with this, I would like to thank you for your kind attentions.
Okay, thank you. So somehow I am hearing your voice has broken. Is it issue with me or your voice is broken somehow? And we lost the
No, it was
connection
fine
for
for us.
last.
No,
Oh, it
it
was
was
fine
fine
for.
for us.
Oh, okay, okay. Then it is maybe my computer.
Yeah, it's internet connection, network connection, I think. Yeah.
Okay, okay. So anyway, we can, I think, start. Are there any questions? I see one question here already from Nanne, Nanne Kumar. Nanne, do you want to ask? PMA arises due to cobalt iron boron MgO interface. Why not from tungsten cobalt iron boron interface?
Well, I do not rule out this possibility because we did not look into this matter very very carefully. But what we believe is that I mean, with our preliminary measurements, we believe that this is originated from the top interface. But we do not rule out this possibility also. Yeah.
Okay.
Okay. Can I hello? Can I ask?
Yes, Sajid, you
Okay,
can.
so thank you. Thank you very much, Himanshu sir. It's excellent talk. So I was wondering about the gate effect on the PMA or say magnetization. So when you apply gate voltage, so if I may, I don't know if I missed. So you talk about the transfer of oxygen somehow. I don't know if it is correct. So do you change your magnetization of a magnetic layer by transferring or doing using the gate voltage? Do you see some or do you expect some change of the magnetization of magnetic layer? Or because when you go in positive direction and when you go to opposite direction, the synchronization or no, or like I don't know, it's a splitting. It's not in the same place. So is it due to the magnetization change or PMA change? What the effect of the gate on magnetization on PMA?
Yeah, that's a good question. So so as you can see, so as I mentioned, there are two different mechanisms here. So at low gate voltages, we observed this change in the effective magnetization of about 14%. So as you can see here is that we extracted these values from the STFMR peaks. So we observed a 14% modulation in this effective magnetization, which since the total magnetization is very high, so it basically translates into a very small tunability in the PMA. So that works at the low gate voltage regime. But if you further increase the gate voltage, instead of changing the magnetization, so basically we need to note here is that there is no leakage current involved. There is no significant leakage current involved in this regime from -3 volt to 1 volt. But as you increase the gate voltage further, so like you can understand from this plot, so this is the high resistance state, which is basically the electric field driven mechanism. But as you increase the gate voltage beyond 4 volt, then you see that this high resistance state switches to the low resistance, which means that there is a formation of the conducting bridge, which was not here, which was not here till 1 volt or 2 volt. But beyond a certain positive gate voltage, there is a formation of the conducting bridge because of the migration of the oxygen ions. And in this regime, in this low resistance state, there is an additional memristive current, which was not present in the electric field mechanism. So therefore, there are two mechanisms. This is the memristive operation and this is the electric field operation. So did I answer your question, Sajid?
Yeah, more or less. I was just wondering about the magnetization of the magnetic layer.
Yeah,
if it
yeah.
is changing with the gate or not. But okay, we can discuss this in.
The magnetization will not change. I mean, because if the magnetization change, then the entire behavior will be very, kind of irreversible behavior then, which we did not observe.
Hello.
So it's based.
There is a question from Rahul Gupta.
Hello, can you hear me?
Yes.
Hello. Thank you so much for the interesting talk, Himanshu sir. Actually, I have two questions. One question is, can you go to slide number 23?
23. Okay, yeah.
Yeah. So if we see the line width versus frequency graph at 0.5 volt, no, not point, I think -3 volt, yeah. So I can see some non-linear behavior of delta H versus frequency. So, and one explanation of this non-linear behavior can be like 2 Magnon scattering contribution.
Well, we basically repeated these measurements. So this is actually not very nonlinear behavior, but see, this you can see here is because if you look at these STPMR measurements are performed in a nanoconstriction, in a gated nanoconstriction of about 150 nanometers. So the signal is not that sufficient, you know. So therefore this error is therefore that's why there is an error bar involved here. So it's not, I don't think this is a nonlinear behavior here.
So you mean signal strength in terms of amplitude or the line width?
Sorry?
So you said signal strength. Is it in terms of amplitude of the FMR signal or STPMR signal?
Yeah, it's a STPMR signal, yeah. Because the STPMR signal is, you know, since the STPMR measurements were performed in a very small region of about 150 nanometers. So the signal is not that prominent as you observe in other unpatterned thin films. So yeah, these are a little bit sensitive measurements in that sense, because and also you cannot apply very high RF power, because then your oscillators, then your devices will switches to the nonlinear regime. So you do not. So I do not want to measure these measurements in the nonlinear regime. So we need to carefully basically adjust this RF power while measuring these, while doing these measurements, because then these oscillators are very prone to switches into the nonlinear regime.
Okay.
Okay.
Yeah.
Okay, I think